Good morning. We were discussing fully differential circuits, and fully differential circuits, you need to set the common mode voltage to be fixed. What value we have to fix it to, we can see. Typically, it is just like operating point, you have to fix it so that you maximize the swing limit, or maybe so that that bias value is suitable for biasing the following stage and so on. So we'll see examples of all of those things. We also saw how to analyze fully differential circuits using differential and common mode half circuits, right? You have to do the analysis twice, but each time with a half circuit. So roughly it's the same as analyzing the full circuit. And functionally it makes sense because you want the desired signals to be differential and common mode to be 0. Okay. So now the first thing, we saw some examples of fully differential circuits, like a differential pair with a symmetrical resistive load and so on. Now, of course, our goal has been to make op-amps which have high gains, and in any high gain circuit, you will need some way of stabilizing the output bias, right? It will get stabilized only because of feedback. Okay, and this is the meaning of high gain, right? What is high gain? It means that it is very sensitive to some changes somewhere. It is, of course, gain refers to change in the output voltage with the input voltage, but any such circuit will also be sensitive to, let's say, mismatches and other things. Okay, so any high gain circuit, you cannot set the input bias and expect the output to be biased correctly. Like for instance, when we had resistive loads, you don't have to do anything to set the output bias. It will get set to VDD minus I naught RL. Okay. On the other hand, if you do have a current source load here, then you cannot easily determine what this is. In fact, in practical conditions, it's likely to be stuck to one or the other swing limits. Okay. So in any high gain circuit, you will need negative feedback. In a fully differential circuit, you will need common mode feedback to set the biases. So now what is this? This is basically the common mode half circuit. This is the single stage op-amp with a symmetrical current source load. Okay, so that we get the differential output. Now, assuming all transistors are in the saturation region, the differential half circuit has the same gain as our single stage op-amp, right? GM1 by GDS1 plus GDS3. That was the gain of the single stage op-amp. That is also the differential gain of this op-amp. Only thing is, this will work only if these voltages are set properly, and that has to be done through common mode feedback. So we look at the common mode half circuit. The common mode half circuit looks like there is a current source here of value I naught. Okay, maybe M1 you can think of it as a cascode for this, right? So this is a current source I naught, and that is also a MOS transistor with some bias at the gate. So now clearly, if VG3 is somehow independent of this I naught, then what happens is, if this current is higher than I naught, this will get pulled up. If it is lower, it will get pulled down. Basically, the transistors will not be in the saturation region. So this has to be biased by deriving VG3 by looking at what is happening here. Okay, this is not a new problem. We have done exactly this while biasing the transistor at a constant current. Okay, so we use the same. So there are many possibilities, but this is one straightforward one. You know that the variation that you get in VD1 is the same as the kind that you need in VG3. So one possibility is to directly connect. Another is through any positive gain amplifier. For example, an op-amp with VCM ref. So in this case, what will be VD1 in this particular circuit? What will it be? VDD minus whatever VSG is required for M3 to carry a current I naught. What will it be here? It will be VCM rep. Okay, basically it will get set to some known value. If you want that, you can use this particular feedback. Okay. So now, how do we, let's say, combine this This is the fully differential circuit. Of course, whenever you do this combination, just like with biasing circuits, right? You may or may not be able to exactly preserve all the features. Some of them may be approximate. We'll see. So the differential half circuit is that. And the common mode half circuit is so the main thing is for the common mode half circuit, this drain of M3 has to be connected to its gate. Okay, right? And in the differential circuit, the gate will be grounded just because of symmetry, but the drain should be left open. Okay. How do we combine these two pictures now? First of all, for a moment, let's forget the differential half circuit. This common mode, for common mode biasing, this drain has to be connected to this gate. Okay. If you want to implement this here, what happens? How will you do it? What do you have to do? That is, you modify this full circuit so that the common mode half circuit becomes that one. What do you have to do? What do you need to do? You understand? I am asking you, this is a partial circuit. Obviously, the common mode half circuit is not this one, right? What is the common mode half circuit of this? The drain and gate are open. Okay. Now, the drain has to be connected to the gate. So, what will happen if you do that here? How do you connect it? So, you will have to do that, right? If you do this, this will be the common mode half circuit. But then what circuit is it? What will be the gain of that? What is the differential half circuit then? What is the differential half circuit? Huh? What happens? I see a lot of air pictures, but just tell me what has happened. So this will be connected to ground also, right? So what will be the gain? 0. So this won't work, obviously. So now the point is, when I say we have to connect this here, what I really mean is VG3 should become equal to VD3. This is also something we have done earlier. Okay. VG3 should become equal to VD3, however we do it. So what modification can I make so that I don't end up with this absurd circuit where I'm shorting the output? So what could I do? This is also something that we have done before, like long back when you did constant current biasing and made a common source amplifier using that. What did you do? Add a large resistor where? So between which terminals? Hey, just say gate and drain. You know what those terminals are called, right? So you can do this. Now, because the gate current is 0, as far as common mode is concerned, nothing has changed, right? No current is flowing through RG. Okay. So maybe, yeah, no current is flowing through RG. So operating point has not changed at all. Now, if I want to realize this in the full circuit, what do I need? So this is just this will get me the common mode. The common mode half circuit should look like this. So what should the full circuit look like? So I should have, if I have RG here and RG there and connect that. So this, now this circuit is the common mode half circuit of that one, right? What is the differential half circuit now? There will be, yeah, there will be RG. Okay. So what is the What is the gain? What is the gain of the differential half circuit? Huh? So it will be GM1 by GDS1 plus GDS3 plus 1 by RG, right? That will also appear in parallel. So we have not got exactly the same gain as before, but by choosing RG large enough, we will get some gain. Okay? Understand? So this is one way of doing common mode feedback. So this circuit here, this combination, I mean this series combination of two RGs, right, between the differential ones. In the differential picture, it will appear like a load RG. Okay? Is this okay? Now another way to think about it is, so basically if you look at only the load structure, so this is so that you can relate this to, I don't know if this itself was a part of the assignment problem, was it? Yeah. So what is the impedance wise? We have this structure. Okay. So now you can analyze it with common mode and differential excitations and evaluate the common mode and differential currents. Okay. So now how do we do this? An easy way is basically just use the half circuits. This is the differential half circuit, right? And then here you have only Vd by 2. Okay. So what will be the current flowing there? So it will be Vd by 2 times GDS3 plus 1 by Rg. Okay. And the common mode half circuit will be that one. And if you have a common mode excitation, what will be the current flowing there? What will be the current flowing? What is the current flowing? It will be times GM3 because this is in feedback. Okay. So you can see basically the impedance of the common mode half circuit is 1 by GM3 and here it is 1 by GDS3 plus 1 by RG. Okay. So another way to think about this load structure, many times this happens. We saw it in the earlier one also, right? So this type of load similar to this. So it gives you a high differential impedance so that you can have a high differential gain, and it gives you a small common mode impedance so that your common mode gain is smaller. So this type of load is one way to enhance common mode rejection. Okay. So we saw this in the other case also. I was just talking about common mode gains. For instance, the difference between these two circuits was that this has inherent common mode rejection. Okay. This one has no common mode rejection at all. But if you have this type of load, then you will have some common mode rejection just because of the load. So this is also used many times. So this is, you could have used this, but I mean, this is a pretty standard way of doing things also. You have something like this and then you have a high differential impedance and a low common mode impedance. Ideally, the differential impedance should have been infinite and common mode impedance should have been 0. Of course, you are not going to get that, but you will get high and low values. Okay. Is this fine? And of course, in this case, the output common mode voltage would be VDD minus VSG3 at a current of I0. That you can get from the common mode half circuit also. Okay. So this works. Of course, this still has a disadvantage. It is still loading the differential picture. Okay. Like for instance, let's say this were a cascode op-amp. So you will get a very high gain, and the reason you get a very high gain is it's very high output resistance. It's not just GDS1 plus GDS3, right? It will be that divided by some large factor. Now, if you put RG in parallel with it, the gain will be determined by RG, not by its own very high output resistance. Okay. So this cannot be used everywhere. Sometimes you can use it. This is likely to reduce the gain. It is of course not short circuiting the output, but it is going to reduce the gain. But maybe it is still useful in some places. Otherwise, you can't get, you can't use very large values of RG. Okay. So this is a particular common mode feedback circuit. We'll see many others, right? Now let's say that I want to use this because maybe I don't want the output common mode to be some value which is dependent on process temperature and so on, right? Because it is VSG3 at a current I0. So it depends on the parameters of this transistor. But let's say I wanted it to be VDD by 2 or some known value. Okay. So I can't use this because I can't guarantee that VSG3 will be exactly that value. But I could use this. If I use VCM ref here, this will be at VCM ref. Okay. Whereas this will be whatever it has to be to carry that current. So now let's say I want to use this in the same circuit. What should I do? So again, so my full circuit is like this without the common mode feedback completed. Okay. This is my circuit and my common mode half circuit. My common mode half circuit is okay. So again, I want to combine these two. What should I do? We'll get into the details of that op-amp later. Let's say we'll use an op-amp, but I want to combine these two. What should I do? How should I implement this? Again, you can think back to how we combined. Where is that? Yeah, how we combined this and that, right? So some similar way. What can we do here? Huh? Wait, do you need it on both sides? Okay, first of all, let's say I want the common mode half circuit of this circuit to be exactly that. What should that look like? No. no. There is only one point to which you feedback. It's not that you have two separate gates, right? You have to provide feedback to this. So what should I do? So first of all, just tell me, like, forget about what happens in the differential mode. I just want the half circuit of this to look like that. So what should I implement or how should I connect it? Resistive divider, where? Okay. So, okay, you went to the final circuit. This is fine. If you do this, I'll still call it RG, let's say. Okay. What will be the common mode half circuit? I don't have the resistor there yet, so where should I have it? So, if this is, let's say, some opamp 1, this will be, I have to divide that half OPA1 for the common mode half circuit, right? This is important when you analyze like loop gains and so on. Okay. And where will this resistor RG be? In series with the input. Okay. So, what will be the output common mode voltage of this circuit? What will be the output common mode voltage of this circuit? VCM ref. Okay. So, this will be VCM ref. So, that will also be VCM ref. What will be the differential half circuit? So, we have this extra load of RG like before. Okay. Right. And the gain is still GM1 by GDS1 plus GDS3 plus 1 by RG. Okay. Only difference between this and the previous circuit is what? Yeah, the output common mode was VDD minus VSG3. VSG3 depends on M3's parameters, whereas here it is some known fixed value VCM ref. Okay. So, we know now how to at least have some options for stabilizing the common mode while getting somewhat high gain, right? We can either set the output common mode to something that is related to the transistor parameters or to a fixed value VCM ref. But we still have to solve this problem of compromised gain. Okay. So, again, there are lots of options. Let's see how to do that. A lot of this will be, see, now essentially we are doing design, but of course, I know the solutions already. So, I am directing you sort of quickly through that. Please go through the circuits. But when you are designing, this is what you would have to do. You consider different options, see which is suitable, maybe combine some of them. Okay. So, now first, before we go to that, how to get rid of this RG, what is a possible option for this OPA1? What should I use? Common source amplifier. What can I use there? What would I use? The first option. I mean, I also want the circuit to be simple, right? What should I use? I can use any op amp. I already know how to design this type of op amps. But what is the first thing I would try? Huh? Huh? You will use an ideal op amp. What would I use? What is my first attempt I would try to use here? Huh? Single stage op amp, right? I mean, that seems like a reasonable thing, right? The single stage op amp works because when will we use a single stage op amp? We need some gain. It is not loaded by a resistor because when it's loaded by a resistor, that single stage op amp type is not very useful, but it is not. And this is for biasing. So, we're not too concerned with swings and so on. We don't expect any signal swings, right? Common mode, in fact, should not be swinging at all. If you look at this, ideally, these two should be swinging equal and oppositely, equally and oppositely, whereas here there should be no swing. So, there's no input swing, the output should also be fixed, right? So, this is the ideal situation for a single stage op amp. Okay. So, let's do that. So, first I'll draw the common mode half circuit and then include the full circuit. Now, I have this resistor Rg. This will be VCM ref. Okay. And then I have my current mirror load. Okay. And I connect it up like that. Right. So this whole thing is that one. Okay. By the way, in the full circuit, I have some opamp, and this I said is half of that opamp. What do I mean by that? What does it mean to say this is OPA1, this is half of OPA1? What does it mean? All the transistor bits are half of what is in the full opamp. Okay. So let me show that with the full circuit also. The circuit will look messy simply because there are many components, but it's not conceptually very difficult. Let me call this MC0, MC1, MC2, MC3, MC4, and this would be connected over there. Okay. And this is my OPA1. In the common mode half circuit, basically I slice off each transistor into half, assign it to the two sides, and then do the analysis. Okay. Is this fine? So first, of course, this hasn't changed anything. Only thing is now we have a transistor level realization of the op-amp. We still have RG in the differential picture. Okay. So the gain is still small. We'll see how to fix that part. Okay. But before that, let's look at some practical aspects of this common mode feedback circuit. Is this clear? The circuit, the idea? All I did was replace the op-amp OPA1 by the single stage op-amp with which we are very familiar. Okay. So now, this circuit, this type of circuit is called the common mode feedback circuit. I think this you already know. Basically, this whole thing here is the common mode feedback or CMFB. So typically it consists of this one, this resistive network. I can call this a common mode detector, right? I mean, very fancy name, but basically all it is doing is averaging the two voltages, right? You have VOP and VOM, and if you have a resistive divider, it will give you VOP plus VOM by 2. This is one type of common mode detector. You can use many other types. Okay. A resistive divider always gives you the average, right? If the resistors are equal. So that part is fine. Only thing is it will load the differential picture also. Okay. And then you have some, you can call this error amplifier if you want. Okay. So basically it looks at the error between the actual common mode and the reference voltage and drives the common mode node, bias node in the appropriate direction. Okay. So this is common mode feedback. Now, of course, so this you analyze using the common mode half circuit. This is the common mode half circuit. Okay. So this is some feedback loop, right? So what kind of, what is the, first of all, whenever you design feedback loops, what are all the things you need to take care of? Stability. Okay. So now is this circuit, is this common mode feedback circuit stable, or is there any concern? What kind of a feedback loop is it? What does it resemble? Yeah. What kind of feedback circuit does it resemble? I mean, we have studied such feedback circuits already, right? How many stages are in feedback? How many stages are in feedback here in the common mode half circuit? How many stages? I mean, how many amplifying stages with a high gain? How many? One stage. Where is the feedback loop? The feedback loop is this, right? That is the feedback loop. Okay. So basically this whole thing. So how many high gain stages are in that, within that feedback loop? One, two. So which are the two? This is a single stage op-amp, right? Followed by M2. What is it? It's a PMOS common source amplifier. This is exactly like a two-stage op-amp, right? Earlier we had an NMOS differential pair single stage op-amp followed by a PMOS common source amplifier. That's what we called a two-stage op-amp. Here also, if you look at what is inside feedback, it is a two-stage op-amp. Okay. Only thing is there is also a resistor stuck here because we need it for the differential picture. So what we really have is this is equivalent to VCM ref and RG in feedback. Okay. Now, if you connect it up like this, can you comment on let's say the step response or loop gain? What will happen? Is this how we had the two-stage op-amp that is nice and well behaved? If not, what is it that we have to add? Huh? Miller, where is that? Where should it be? We had another component, right, in our two-stage op-amp. I mean, if you think of it as an integrator, the GM1 was the differential pair, and then we had the integrating cap. Or if you think of stabilizing it using a Miller capacitor, there is another capacitor. But where should that be now? Between the gate and drain of M2, basically across the second stage, right? So we will need to have that. I'll call it CCCM, right? Some capacitance there. Okay. Right. Now, of course, we did this using looking at the common mode feedback circuit. We said we need this capacitor so that the common mode feedback loop is well behaved. What does it mean actually to be well behaved? What happens if we don't have this one? What is the big deal? Okay, I don't have this capacitor. What do you think happens? So they'll be ringing of the common mode circuit. But yeah, what happens is it could happen when you power on the circuit or when there are some changes. So, but if you think of let's say a small step in VCM ref, you expect that ideally they should just follow that. Okay. But here what may happen is it will do that. Now, what happens in the differential circuit? On both sides, this is common mode, right? So, on both sides you will have this. The bias takes a long time to settle. Okay. That is one possibility. or it could even be outright unstable, right? Because this is not just two stages, meaning this op-amp itself has the equivalent feedback loop. This is not OPA1, this is OPA1 plus the second stage, right? This is basically a two-stage op-amp that has two poles, and then you also have this RG and you have the parasitic capacitor here. So you have a third pole as well. So it is possible that it is outright unstable. So that means the bias will never stabilize. Okay. So you can have a circuit, differential picture, there is no problem. Common mode, it can be unstable. What it means is you power on the circuit, both sides, the whole circuit will be oscillating in common mode. Once the circuit is unstable, it doesn't matter what frequency it is oscillating at, what frequency you want to use it at, and so on. If it is unstable, you can't use it. It's not that, hey, it is unstable, the poles are at 1 gigahertz, so I will use it at 1 megahertz. No, if it is oscillating at 1 gigahertz, what it means is that it will also go into, how does the oscillation get limited? The transistors will go into the triode region and so on. So you can't use the circuit, that's all. So this has to be well behaved. So which means we need to have this CM over there, okay, in the common mode half circuit. Of course, common mode half circuit is some representation. The actual circuit is on the left side. For this to appear here, what should happen in the actual circuit? For that CM to appear in the common mode half circuit, what should I do to the fully differential op-amp circuit? What should I do? Yes, what should I do? I mean, think of how you go from here to there. Any component there should be reflected here, right? So where should it be? Yes, Gunasekar, what should I do? Where? Basically, anything here should appear on in both halves. So okay, so that's basically what it is. So this also gives you like, I mean, this is something known also, but another picture of any of these stabilizing circuits. What is really happening at low frequencies? The feedback goes through this entire amplifier, okay, and it takes a long time. There is a delay through the amplifier. So a way to fix that is to provide fast feedback directly to the gate. Remember, one of the earlier circuits was just this. You give feedback directly to the gate, right? That is, we were just shorting it directly to this gate. Okay. So now, of course, we can't do it for DC, then it will kill everything, but we do it only for high frequencies. So at high frequencies, you essentially have a fast path here. Okay. So that's another way to think of any of the stabilizing networks. Like I think I had mentioned this. Eventually, all well-behaved feedback systems will have only one stage in feedback. Okay, at high frequencies, that is around the frequency where the loop gain goes to unity. One way or the other, you will end up with only a single stage in feedback. Basically, the bottom line is we only know how to make single stage feedback circuit stable. Okay, so you reduce everything to that. Okay, so this is true of Miller. This is true of feed forward. Okay, in a feed forward stage also, around the frequency where the loop gain is going to unity, it's only that feed forward, that single stage that is active. The other stage is there, but it's not providing any gain. So here also, basically you have a fast bypass path here. That's another way to think about it. Okay. Is this fine? So now what happens, this will have an implication on the differential picture. What happens because of that? This, anything you connect here can have an influence on the differential picture, right? So what happens there? So you have CM in parallel with this. Okay. So that will add to the load capacitance of that stage, and it will move the pole to lower frequencies. But it is something that you have to live with. Okay. Any questions? So now in fully differential circuits, your common mode feedback is like a single-ended feedback circuit, and you have to do whatever you do to, I mean, everything that you know about negative feedback and stability, you have to apply to that and make sure it is well behaved as well. Okay. And of course, you should try to design the common mode feedback so that it affects the differential picture as little as possible. Okay. Now we have actually another problem here that I already pointed out. We have this parasitic capacitance. Okay. So there is another pole, this Rg times this Cp. How might you fix this? Again, you can think about one of the assignment problems. You have, if you have this Rc, okay, if the R is large, here we do want large R, right? We don't want to affect the differential picture. This Rg will be large. We have large R, and then the pole tends to be at a lower frequency. Okay. So now that means that at high frequencies, that is beyond the corner frequency of this RC network, you have 90-degree phase lag. Okay. So if you don't want that, what is it that you can do? Huh? No, that you can't do, right? That you can never do. That C is not something that you deliberately put. It is the result of whatever component appears there. I mean, again, one of the assignment problems dealt with something like this. If you have a pole that is providing a lot of phase lag, what is one of the ways to combat it? What can you do? Or to avoid high frequency phase shift, what is it that you can do? In one of the assignments, you had this problem, right? You had a transimpedance amplifier operating from a photodiode. So now, because of this parasitic, due to the diode also, you could not increase Rg to large values. So how did you fix this? So you add a capacitance in parallel. Okay. Why does this help actually? This capacitor, why does this help? What happens at high frequencies? What is so special about this capacitor? At high frequencies, it's a capacitive divider. It does not have phase shift. Okay. R and C will have 90 degrees phase shift, well beyond the cutoff frequency. Whereas C and C will have 0 phase shift. Okay. So that is the advantage of this. So you may have to add this also. How would you do it? What do you have to do in the circuit? So you can do this. Now there are few different options. These are things that you have to try, then see which one works best. You also would like to add as little capacitance as possible. So one is you add a capacitance separately here. Okay. What does that amount to in the full circuit? Across Rg, you can add that. Okay. These are all different design options you have to see. Now, you may say, already have some capacitors there, right? So I could potentially connect it up. Okay. You could try that also. Well, actually, sorry. In this case, you can't do that. I think, no, this won't work. This won't work at all. Ignore that. It has to be this one. Why will it not work? Then the amplifier is not doing anything because you have DC feedback directly from here to there. The amplifier is shorted from the input to the output. In this case, that won't work. Okay. What can work is, instead of having a capacitor here, which will directly, now you have this capacitor and that capacitor loading the differential picture. What you could potentially do is this and that. Okay. So that is another possibility. That is, you have capacitors here. This is symmetrical, and then you have this. Now, this capacitor does not appear in the differential picture. Okay. So that's what I want to do. So there are different possibilities. This is all engineering. So there are different options, and you can think about it. I mean, if you these also, like, the solutions you look for depends on the problems you face. As you are designing, if you find that this pole is a problem, then you try to do something about it. Okay. Is this clear? So we have many options. I mean, one of the things that happens is when you have a common mode feedback with some error amplifier with an op-amp, then the amplifier may be a single stage, but the common mode feedback loop will have two stages. So you have to do whatever it takes to stabilize it. Of course, the earlier one where we just had resistors, here you did not have to do that. Or here also sometimes, maybe if the resistance is very large, you may need to do that, so that you don't have ringing in the common mode. Okay, because here also depends on the value of Rg and the parasitic capacitor. This can also be a second order system. You will have some parasitic capacitor there, you have Rg here, and you have these two capacitors. So now, to make it closer to a first order system, you will have to connect that. So that may be required. Okay. So basically, if Rg is one way to think about it, if Rg is very large, the path through Rg will be slow. Okay. So you bypass that with a capacitor so that it becomes fast. Right. This you can evaluate. If you have this Rg, where will be the poles of the system? You can evaluate the impedance here. Okay. You can evaluate the impedance looking into this, and then you will see that it can potentially have ringing. With the right value of Gm and Rg, you can have ringing. Okay. So common mode wise, yeah, we have many options now. Things are sort of working, but differentially we still have the same problem from the beginning. That is, Rg loads the differential picture. Okay. So now we would also like some way to fix that. So let's see how to do that. So let me remove some of these distracting details here. We will need that, but just to avoid clutter in the diagram, I'm going to remove that. Okay. So now let's say this is VOM, this is VOP. What is this? What is that voltage? The output of the common mode detector? VOM plus VOP by 2. Okay. What are these currents? Currents through MC1 and MC2? You can call it GMC1. What were those currents? So it is GMC1 by 2 times this difference voltage, and here it will be minus GM1C1 by 2 times the same differential voltage. Okay, so let me just write the expression for one of them. That current would be G1CM by 2 VOP plus VOM by 2 minus VCM ref. Okay, and the same current will be in the upward direction on the other side. Is this part okay? I'm just saying it is that GM times the difference voltage, that's all. This is something that you know. Okay. Now, what we would like is, if we generate these difference currents, however we do it, the common mode feedback will behave the same. That is, let's say we have this resistor plus this differential pair. The purpose of that is to generate this particular current, right, which is being fed to the current mirror load. However else we generate this, we will get the same result. Okay. So let's say I remove all this. I don't know what I'll put, you can figure out. I don't want the resistors, but I want some box here that will provide me these currents. And what should these currents be? GMC1 by 2 times VOP plus VOM by 2 minus VCM ref. Okay. If I do that, this circuit will behave in exactly the same way as the other one. Now, please try to generate these currents. You know all the basic circuits, both the active circuits, passive circuits, etc., without putting resistors between these. Okay. So, we'll continue from there. Is this clear? Any questions? Yeah, that basically, you know the loop gain, right? So, you will have to choose it so that that common mode feedback loop gain will have a dominant pole behavior. Okay. So, you can calculate it, but there are many poles and so on. The bottom line is, just like in the assignments, you choose the smallest value of CC that gives you the dominant pole behavior with sufficient phase margin. But you can calculate it. Basically, the unity loop gain frequency of the common mode feedback loop must be sufficiently smaller than the non-dominant poles and zeros. Okay. This is fine. Please think about this. This is some small exercise in design. You can try to manipulate some circuits so that you get this.